It's Alyssa here. I had this on earlier today, but it is afternoon. Actually, it's closer to 6 o'clock. It's 7:15. Oh, I really thought that I was going to be inside the house by now. Holy crap. Okay. Hey, it's been an interesting day, a long day, but we were talking about the speed of sound. So let's get into it because it's just easier that way. Oh, hi, Robert. Hi, Andreas. Sorry, sometimes I can kind of forget to have that little bit of, oh, what do you want to call it? Um, Niceties. So, all right, the speed of sound. So, when we are uh, anybody that is an engineer, anybody that's going to be flying a plane, this is what NASA says. As scientists and engineers, we work to reduce aircraft noise. A thorough understanding of the physics of sound is necessary. The speed of sound and how that speed depends on certain variables are more important concepts related to the physics of sound. Engineers who design every aspect of an airplane from the airframe through the engine must have a thorough understanding of the speed of sound since noise affects each component of an aircraft. So if you think of, first of all, acoustic baffles, be in a gymnasium or a busy restaurant that doesn't have the ability to dampen sound. Now, in a gymnasium, I have a hard time. Oh, here's a better example. I went to Las Vegas and we were at Circus, and there's all this casino noise. And I laid down in bed that night after being there for most of the day because my husband's father was winning at a quarter slot. And then he would lose and then he would win. But he loved it because this cute little lady would come over with his Captain Morgan and Coke. So he stayed there all day. So when we came home and we laid down, all we could hear was that ching 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 in our ears, but we weren't physically there. It was like a phantom sound. So is that the yeah, I just think extra noise like the gymnasium or a busy restaurant, it's so hard for me to understand, especially if somebody's speaking Swedish to me. It really needs to be quiet. Yeah, that's much better. And maybe it's because that's why I work in a really quiet environment. But I work at a school also, and I'm like a substitute teacher helper. And I tell you, sometimes after the end of the day, with all the craziness of the kids when they're outside or inside, um, I just need to sit in the car and just breathe and just relax. That noise, that extra noise. So acoustic baffles are used in office settings. They're used in all sorts of in nice upscale restaurants so that people can have a quiet, nice conversation with somebody actually fairly nearby. So the speed of sound is important, and dampening that is actually nice because then that extra noise is doesn't vibrate as much, and the aircraft obviously can stay together. So let's just go here. Oh, it won't let me. All right, so I'll come back. Okay, so now I'm going to share what I was trying to click on that it wasn't going. So yes, this is for grades 9 through 12, so high school. And that's just my speed. So here is NASA's information about the speed of sound. And this is the lesson overview that pretty much I just read to you. So it talks about the objectives, background, and this is what I want to bring up. Let's see, can we make it bigger? Yeah, maybe. Yeah, there we go. Look at that. I don't know how to get rid of this over here. Sorry. Okay. So the speed of sound in the air is slower than it is in solids and liquids. And to some, this may seem counterintuitive, but air is a gas. And very importantly, property of any gas is the speed at which sound travels through it. The speed of sound is actually the speed of the transmission of small disturbance through a medium. So if we have a medium of air, the speed of sound is 331 meters per second. In seawater, which is salty, it's 1,000. And then solid steel is 5,180. And then this is in miles per hour at 70 degrees. And why this is important, obviously we have altitude, and altitude affects the speed of sound. But let's go back to my first thing that I was sharing. And this is the speed of sound in salt water. And it's taken from Wikipedia, but like I've talked about, I'm collecting all this information from various sources. And the more collection that I have, and then I can weed out, but the more collection that I have, it's easier to interpret and make a decision. So I'll get to the decision later. I guess you'll be the decider. But the speed of sound from Wikipedia says sound varies with water temperature, salinity, and pressure. The speed of sound in seawater is about 1,500, where we just saw, whereas the speed of sound is usually 330 in the air, which we just saw. The freezing point of seawater decreases as the salt concentration increases. The salinity in isolated bodies of water can be considerably still greater. And then for me, I took some information from the tables that were on the Wikipedia. The saltier something is, the less it conducts heat. Now that's interesting because we have a lot of salt in our body. The higher the ambient temperature, the more conduction of heat. Yeah. Metal is used for cooking. It conducts more heat when temperature is raised. So metals have a high thermal conductivity. Styrofoam is a low thermal conductivity, and it's very inefficient at conducting heat. Therefore, styrofoam is an insulator. That's another segment that I'm not going to get into when we're talking about insulators. But the thermal conductivity decreases with increasing salinity, and it increases with increasing temperature. And this is the point that I wanted to make. When we increase salinity and we increase temperature, then thermal conductivity. Oh, wait, thermal conductivity decreases with increasing salinity, and thermal conductivity increases with increasing temperature. Yeah, well, but basically, the speed of sound varies with water temperature, salinity, and pressure. And I actually think, but I don't know for sure. I think pressure and temperature have a lot to do with each other. Because the higher the pressure, the higher the heat. And this is why we use a high pressure cooker in our house. And a high pressure cooker, in a smaller amount of time, we can actually cook a chicken because we increase the pressure, and so the heat goes up. So when we're increasing pressure inside the body in some fluid-filled spaces, this isn't good for the eyes. It's not really good for the ears, because I can tell you, if I've been in an airplane and my ears haven't adjusted to the altitude, it hurts. Hurts. And also, pressure of the eye has to be just right. And we have high glaucoma, high pressure glaucoma, and low pressure glaucoma. And both are very delirious. Both delete the ability to see. Deleterious, maybe that's it. All right. So everything needs to be lagom. That's a Swedish word. Hopefully you'll know that by the time. And it's lagom is just right. It's not about balance. It's about being just right in the right proportion. So somebody serves you coffee, you can say lagom, which means I don't need any more. You can stop pouring. Yeah. And then that gets us into tensional integrity. And when we talk about tensional integrity, that has been taken over to biotensegrity. And to have a tensegrity unit, it has just the right components and just the right pressure to form a shape. So anytime that we have the suffix ity, it comes from French, I believe. That is a suffix that comes from French. And then, so if we want to have good integrity, then that means our tension is in the right proportion. And we, as body workers, can help change the tension, which means we're changing the pressure. And pressure is a sonic force. And the sound wave is that. And this is why we talked about the elephants. And Caitlin O'Connor and her team for 20 years studied elephants in Africa. And I'm going to put in the show notes that information. But these elephants can decide, they know where the rain is because they can feel the thunder. And elephants notoriously have been known to know that an earthquake is coming and will move out of the area because they're grounded to the earth, but their feet splay out when they step. And those Pacinian corpuscles really give them a lot of good information. They can even tell approach of a predator. Now, they use their hearing, and it's thought maybe they understand certain language types because if there's a certain predator, people that want to injure the elephants, they learn certain dialects and clicks and speaking, but they also know when a friend is approaching. So they're really smart. They're not the only smart animals out there. Something really interesting. You know, we talk about everything being wet and needing to be wet, and we're going to talk pretty soon about eyes, which is definitely an amazing thing, and ears. But when it comes to the eyes, we had a Swede here in Sweden. He wrote his dissertation in German. So, hey, both Robert, you and Andreas can read it if you want, but it took 10 years to have him be taken seriously. So he's a Swedish ophthalmologist, best known for describing the eponymous condition Sjogren's syndrome, which the original name was Zika syndrome, and Zika, I think, was Latin for dry. So dry eyes. So he was born. He was born in Sweden. And the interesting thing is, he wrote his doctoral thesis in 1933 on Zika syndrome. And he wrote it in German, and this is the title, not going to say it, but in English, on knowledge of keratoconjunctivitis Zika. And it wasn't until 1935 when well, let me back up. He wrote this, and the Karolinska Institute denied it and said, no, you need to do more work. We're not gonna approve this, and so you don't have a job in academia. So he moved on, and 2 years later, he moved to a hospital where his wife to work. He's working in a hospital, and his wife already has an established clinic, her own private eye clinic. So a year later, the name Sjogren's syndrome from Zika syndrome is gaining traction. And then 1940, an Australian translated his thesis into English. So 1936, somebody renamed Zika syndrome Sjogren's syndrome. 1940, an Australian translated his original thesis from 1933 into English. And by 1943, there was worldwide medical acceptance of Sjogren's syndrome. And what is that? Yes, okay. For anyone that doesn't necessarily know, I understand. But this is in Swedish, sorry. It's primarily, oh, 90% of patients are actually female. That is an interesting thing. But the syndrome, Sjogren's syndrome, is an autoimmune system disease. And it has its roots in the body's exocrine glands. So the saliva and the tear ducts. And they become inflamed and they diminish in function. And basically it's because they're dry. So they're not working. And this is changing everything in the mouth, it's changing the eyes. And he knew that this was a problem, but it took 10 years to get it going. But nowadays it is pretty much a rheumatoid group. So it's in rheumatology. So if you're in rheumatology and somebody presents with Sjogren's syndrome, then they're treated in that specialized field. Dry. Nothing wants to be dry. And then let's go to the eye, because oh my gosh, talk about the coolest thing. Here's the eye. And yes, I have some information about the eye that no, that's not what I wanted. So when I read Neil's paper, and Neil and others, about the pancreas, he has this term SI, and I believe it's interstitial fluid-filled spaces in this reticular network. And then I started reading about the eye. Well, I read about the eye before that. There's something I'm not going to share, but it was cool. It had to do with a virus from Ian Trojer, and he went to help people with the Ebola virus. And so he came back to the States and he was cleared because they did all the blood work. But later on, when there was so much pain in his eyes, finally went to an ophthalmologist and they actually took the fluid from his eyes to find out that the Ebola virus was living in his eyes. And his eye color changed. So both eyes were the same color, and then one changed to blue and one was green. I mean, pretty freaking cool. So I digress. But here's about the eyes, the virtuous body, which I think is kind of cool, because the virtuous body, the glassy body, is really what the eyeball is called. So in humans and other vertebrates, the virtuous body, aka virtuous humor, also spelled humor for everyone in England, it's a clear gel that fills the space. Here we talk about fluid-filled spaces. It's in between the lens and the retina of the eyeball, the virtuous chamber. So fluid-filled spaces, and even the eye is fluid-filled. And it's a space. The virtuous humor contains no blood vessels, and its volume is mostly water. So it consists of salts, sugars, virtuosin, which is a type of collagen, a network of collagen type 2 fibrils, glycosaminoglycans, hyaluronan, optosin, and a wide array of proteins. I mean, these eyes of ours are like mini fascial systems, right, Robert? I mean, when you read that, that's what the fascial system is. And the biochemical properties, this comes from Wikipedia, they contain very few cells, and its composition is similar to that of the cornea. The virtuous humor is composed mostly of phagocytes, which remove unwanted cellular debris, and halocytes, which turn over the hyaluronan. The virtuous humor is viscosity 2 to 4 times that of water, giving it a gelatinous gel kind of consistency. And it also has a refractive index, which doesn't mean much to me, but maybe it means something to you. So I'm reading Neil's paper, and he has IS, fluid-filled spaces, and this is evidence of interstitial continuity within the and beyond the human pancreas. So these fluid-filled spaces, although they are small, they are vast. They're numerous. There's so many of them. And just like our P01 and P02, they are small. They are small, small, small. And Ardem Pataputian says how small they are, but I would get it wrong, so I'm not going to go there. And the thing is, it's not just one ion channel that opens when pressure is delivered. It's thousands. And that creates chemical flow and ions to flow through and enzyme activity, and electrical signals. So this fluid-filled space, although contents of the large interstitial fluid-filled spaces in particular have not been fully studied, yes, all interstitial fluid-filled spaces contain hyaluronan and collagens. Most also appear to contain elastin, glycans, and a variety of glycosamides. Didn't we have that? I mean, that sounds just like the eye. Collagen type 2 fibrils and glycosamine hyaluronan. Wow. Recent studies used the hyaluronan binding protein, and given that hyaluronan is highly hygroscopic, I don't know what that is, and would support fluid flow, albeit slow fluid flow. These studies supported the concept of a body-wide network, showing that all interstitial fluid spaces are continuous with organs such as the skin, colon, liver, and adjacent tissues, such as skin, and its underlying subcutaneous fascia. Which, if you think about it, we're gonna go down and we're gonna skip a little bit here because it talks about a cavity. The virtuous cavity. Where did that go? Oh, the virtuous chamber. It's between the lens and the retina of the eyeball. Okay, here we go back to Neil's paper. So it's between adjacent tissues such as the skin and its underlying subcutaneous fascia, as well as colon and its sub-adjacent mesentery. Moreover, adventitious sheaths. I know my anatomy, that has more to do with blood vessels. And the perineurium, which is the covering around nerves, contain interstitial fluid-filled spaces that are also in continuity with the tissues through which they pass, and thereby provide body-wide continuity along the entire cardiovascular and nervous system. So that was the only thing that I copied from his paper, but that's it. So there are about 126 million photoreceptors in the mammalian eyes. For phototransduction. So we talk about mechanotransduction with all of our mechanoreceptors. And Robert, you talked about this, 250 million. And we have about 120 million photoreceptors, mostly the classic ones, 6 million cones and 120 million rods. Each human retina. So, okay, so each human retina, so you have 2 retinas. So let's just say we have the same number of photoreceptors, rods, and cones in the eyes that we do in the whole body with mechanoreceptors. That's huge. And there is a third photoreceptor, intrinsically photosensitive retinal ganglion cells, and they're discovered in the 1920s. These cells are thought to have a role in treatment of circadian rhythms. Cool. So here on another source, Cleveland Clinic, aqueous humor and virtuous humor of fluids found in the eye. These are bodily fluids located in the eye that may be made up of water, but have other components that nourish and protect the eyes. Virtuous humor also salts, sugars, proteins, and collagen in addition to water. Phagocytes that are cells that keep your eyes clean. Along with the water, aqueous humor also contains acids, electrolytes like sodium, potassium. That would make sense because our muscles have sodium potassium pumps, and that's in the body. It has azelaic acid, vitamin C, glutathione, and immunoglobulins. The virtuous humor is responsible for 80% of the volume of the eye. That's pretty cool. And it's viscous, but it still lets light through. One definition of the word humor is a bodily fluid. The eyes continuously make aqueous humor. And that's the clear fluid in front of the eye. So continuously, always, it's like our software, it's always updated. So the aqueous humor keeps the eye inflated and provides nourishment, and it also provides the right ocular pressure. Glaucoma, right? And macular degeneration. So when this is out of balance, it can no longer allostate for some reason, it can't reproduce itself, then we have macular degeneration. The virtuous humor provides nutrients to our eyes and helps keep eyes the shape of the eyeball. So our vision does change when the shape changes of the eyeball. And it makes a space between the lens and the retina. This is the virtuous cavity that I was talking about. This is between adjacent tissues. These fluid-filled spaces that we have in the human fascial system and interstitial continuity is the same thing. It just, this is in the eye. It's called a glassy cavity. And this is a fluid-filled space. It seems to be the same thing, just different words. The function, the virtuous humor sticks to the retina. So it's sticky. It's adhesive. But also with this fluid, like we do in the fascial system, there's a certain slide and glide. And I think it was Helen Lagerson that was talking on one of her talks. And she talked about a sandwich. And if you don't put any butter on the sandwich, then it's dry. But if you put butter on it, then it slides. And so I'm thinking of peanut butter. I love peanut butter. Peanut butter sandwich. You put peanut butter on 2 pieces of bread, it's stuff. But if you put a fatty, sugary jelly in between, then you have the broth. And what we're trying to do as massage therapists and body workers is to continuously have these fluids being bathed all over in our fascial system. And I find it interesting. Eye exams are everywhere. We have eye charts and color tests, and then we have these visual field tests. So how well the eyes move and how far we see from either side. So like a peripheral vision. But we don't move our body. We move our eyes. And there's a special test for this. And so, yep, the provider might use a computer or their finger and just move it side to side and compare it close. And that's studying the brain and sight and how everything's communicated. But where are the tests for the fascial system, for our proprioception? Why don't we have something like Dr. John Berkowitz talks about with NASA, with osteography testing? And then I had some questions. Sound wave is a sonic pressure. Salt water increases the speed of sound. Density also increases the speed of sound. So in air, the speed is in salt water, it's fast. Salt water, it's faster. And in the ground substance, the example was metal in NASA's thing. But if you think about what the elephants are doing,
It's in the actual earth that the vibrations, the seismic communication is traveling. And then I have to wonder, we have high weight hyaluronan, low weight hyaluronan. I just have to wonder, Robert and Andreas, does it have anything to, is it similar to the high pressure glaucoma, low pressure glaucoma? Because our body has halocytes that make hyaluronan all over it. And hyaluronan is ubiquitous. It's present before birth. And bacteria use hyaluronan as a cloaking device. So, and they use this cloaking device because the immune system doesn't see it as a threat. So the immune system won't react to these bacteria. And the bacteria are the flesh-eating bacteria. And I'm sure there's other bacteria that are on your skin that use hyaluronan because it's ubiquitous, it's present before birth. And so is the body's way, is hyaluronan being used to amplify the signals traveling within our ground substance and our fluid type spaces? Because the speed of sonic pressure changes in density and in fluid. So part of me wonders when things get dense, like the pancreas. Maybe you want to see Patricia Keeley. So Patricia Keeley, I won't be able to remember it, so I'm going to go there. But the joint conference, Robert, you were there. You stood up at the panel discussion, so you might remember this panel discussion. But Patricia Keeley was talking about the pancreas and how cancer can be treated in the pancreas using hyaluronase. So it breaks down hyaluronan because she says the problem with pancreatic cancer is the hyaluronan has got so dense, so so dense that the the drugs to fight cancer can't even get in. So I found that very interesting in her talk, and let me just find her. So yeah, Patricia Keeley, Professor Chair, Department of Cell and Regenerative Biology, University of Wisconsin. She received her PhD. Dr. Keeley joined the faculty of Wisconsin 1999, is now Professor and Chairman of Cell and Regenerative Biology at University of Wisconsin. She's co-leader of the Tumor Microenvironment Program, and her laboratory investigates how collagen-rich connective tissue changes surrounding tumors. They found that collagen becomes aligned and bundled, and that this change facilitates the breast cancer invasion spread. Oh, yeah, and I remember if you go to that panel discussion, she talks about how hyaluronan is smart enough that it basically makes its own fake blood vessels because it makes channels. And that's cool, isn't it? It's just funneling the nutrients towards the cancer and the tumor. And hyaluronan does that. So there was a term that she used. Fake blood vessels will go up. And unfortunately, Dr. Keeley is no longer with us. Ironically, today. I think one of the greats too with Thomas Finley had a similar fate. Just too bad. Hey, so I found it. I just thought it would be easier to show you. So this is Patricia Keeley talking, and I would say around 16 minutes. She also talks and she gives her opinion about what it is to be at the conference. But why aren't we doing something before we get cancer so that we can do some yoga? Or she felt like she should go back to her yoga class and take more yoga to do early interventions before changes happen in the body. And then let's hear her about this vascular mimicry.
Manipulating or acupuncture or something. I don't know because I don't know that area, but that's something about hyaluron. And the other thing is that there's something called vascular mimicry, where tumor cells actually line fake blood vessels to help get blood supply to the tumor. And part of what they do is they coat themselves with hyaluronic acid, and that prevents them. That helps create this fake blood vessel that works as a blood vessel. And then the last thing is that hyaluronin is implicated in metastasis. And one of the genes we see go up in the tumor cells when they're in a stiff environment is the receptor for hyaluronic acid. So that receptor allows the cells to migrate more and invade more. So it's definitely involved. Now, how do we use that for, acupressure, acupuncture, other forms of approach, chiropractic? I don't know. I just know it's there and it's important.
So if you're interested in hearing what she has to say, because the transcript isn't available, right before the segment that I started playing, she describes what they're doing in their lab with hyaluronin, gets the enzyme that breaks down. You know, let's see. Let's get on to hearing. I had so much that I was going to share with you. This is a great book. Small text. So I'm going to see what I can do with this. But we just talked about eyes detecting light waves. So we have the ears. And ears are hearing the sound wave. In a moist environment with cartilaginous funnel, collecting sonic vibrations in the air. So this book by Nina Kraus of Sound Mind details the hearing process and learning to interpret pitch and cadence and timbre, especially if you're a singer or if you are somebody that riffs on a guitar. And I have a babblefish, but from Hitchhiker's Guide to the Galaxy, I have a babblefish, but my daughter's babblefish learned a lot faster than my babblefish for the Swedish language. But finally, I had to interpret the sounds and then put meaning to those sounds. And there's something in neuroscience called the binding. And how do we give meaning to what we hear? It's still a question. But the binding problem is how a person determines meaning from sonic air pressure, which sounds like the craziest thing. But we all have sonic air pressure and we use it all the time. So in page 35 to 57, page 39 to 57 in this book, she has an eardrum, a thin collagenous membrane that vibrates sound waves, and when it inflames, it hurts. If we think of the eardrum like the ecosystem of the bugs on our hand, it's not well when it's inflamed. The environment is not good. Air pressure changes can cause pain, and the three bones can function, yet sound is muffled. It's not clear. It's hard to determine what people are saying. The eardrum vibrates from sonic air pressure. The eardrum pushes on the anvil bone. The malleus is the anvil. It taps on the hammer, the incus. The stapes taps on the second membrane of the ear, oval window of the inner ear. Fluid begins to move because of the second membrane and that physical tap. And then dense fluid on the other side of the window moves. So we have fluid in different densities. And this allows for hearing. But if everything is dry, if dry, no hearing, no air movement alone, like that, will not move fluid. It needs all of those things. It needs the bones. It needs the membranes, those windows. And if the fluid is too dense, then also the wave doesn't move and that next number doesn't open. but the three bones amplify the power of the fluid flow by a factor of 20%. So those three bones that we mentioned, fantastic. And then hair cells along the cochlea feel the rush of fluid caused by the stapes tapping on the oval window. And then here it talks about the inner cochlea. And if we look at a gecko and with their feet, they have so many different ridges and grooves. And our hair cells is about 30,000. This physical force opens ion channels in calcium and potassium of mechanoreceptors. Mechanotransduction is a physical force that creates an electrical signal. This electrical signal excites the auditory nerve. Auditory nerve is 30,000 fibers bundled together. The nerve is tuned to a specific frequency. The speed of nerve conduction slows as it travels through the brain. The signal hits cells in the cochlear nucleus, but bush cells, cartilage cells, octopus cells, yes, octopus cells. But hearing depends on the entire process, the entire hearing and ear process working together as a unit. And this is just one sense. This isn't even our body and our fascia system that we're talking about with all the mechanoreceptors. So electrical signals from both ears travel to the midbrain, the inferior nucleus, and all auditory afferent synapses in this midbrain structure. So, yeah, these signals are strong and they're measurable on the scalp. So, even if the tympanic membrane, the eardrum is not working, you can know if the bones are moving, and you can also measure these auditory afferents in the midbrain structure. The inferior cochleus is a midbrain structure that integrates most of the ascending auditory information. The midbrain projects ascending auditory information to the thalamus and then on to the auditory cortex. The auditory thalamus leads to the auditory cortex. The auditory thalamus is auditory responsive portion of the thalamus. It's called the medial glycinate body. The thalamus, as it relates to processing acoustic features, is important for speech perception. Focusing on the thalamic nuclei that relate to auditory representation of language sense. And I tell you, this one was really old in me and not my daughter. But here's the cool. Auditory cortex is the final place for actual sound recognition. Signals from the right ear, my right ear, travel to the opposite side of on the brain's left side. And then, only then, afferent or descending signals dictate behavior and mood depending on the quality of the afferent information. It's a doozy of a book. Doozy. So I did. Something I don't know. So for anybody out there, if you want to see what we were talking about, there's the tympanic membrane, there's the middle ear, and gee, where are, oh, those tiny little things there, that's the bone. There's the stapes. Can't see it very, that's the malleus and the incus. It's a complex system. And basically, you know what? This tuning fork, it can be heard and it can be felt. So I'm going to wind up. M, M, M. Mandy Harvey. Mandy Harvey. Okay, I'm sharing it with you. Now, Mandy Harvey was on America's Got Talent in 2017, and I will put that in the show notes, but it is definitely something that has to be watched. And the thing is, at 4 years old, she always wanted to be a singer, and she learned to sing at 4 years old and tune and pitch. And unfortunately, she got a connective tissue disease. So with this connective tissue disease, she could not hear anymore. Now, we talked earlier about wants, needs, and desires. And because we have this emotional, wonderful regulation system, this want and desire came through so that she could learn. And she has a wonderful song that she won with called Try. And if you have a chance to listen to those lyrics, please do, because it has gotten me through some really dark times. And I listen to it daily. No, I listen to it a lot. Anyway, here we go.
She said, Dad, I can't remember what your voice sounds like anymore. At that moment, you knew that things would never be the same.
Everything that I had ever wanted was just going away, and I couldn't stop it.
The music is alive inside of her. The only question was, what could she do with it now?
My dad suggested that we play a song. I said, well, that's crazy. But I had a guitar tuner, and I hummed my starting note and just went for it. Music now isn't about the sound.
She said, Dad, I can't remember what your voice sounds like anymore.
Oh, so music now is not just about the sound. It's about the feeling. She sings on stage with her shoes off so she can feel the vibration in the earth, exactly like the other. And she's beautiful. That is amazing. I love it, but I won't play it because they could copyright it. So there we have Mandy Harvey with the golden buzzer. You can see that her shoes are off, and everyone's asking her questions, but she plays and
I'll try.
she plays the song "I'll Try," and you know what? I tried. This was 2 years ago. It's all rights with this video is from NBC, so it'll be copy struck if I play any of it. That's it. So good. Bye for now. Hey,